Hey guys, Algo Speed here. Welcome to the first video in this Quant LeetCode series where I'll be covering LeetCode problems that are frequently asked from other quant firms. So here we have this problem 295, find median from data stream, and this problem was asked by Amazon Uber, but it was also asked by Citadel as well. So in this problem, we're told that the median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value. And so the median would be the mean of the two middle values in that case. So for example, we're given this array 2, 3, 4. The median in this case would be 3. However, if this array was an even length list, for example, 2 and 3, we would want to return the mean of the two middle values, right? So we would want to return the mean of 2 and 3, which in this case is 2.5. So our goal is to implement this mean finder class, which has a constructor median finder class, which has a constructor median finder, which will initialize the median finder object. And this median finder object has two associated methods with it. The first method is an add num method, which doesn't return anything, but takes in an integer num from our current data stream and adds it to the data structure that our class will implement. The second method is this find median method. It has no inputs, but the return value is a double in this case, and it returns the median of all elements so far. And the reason why it's a double is because even though we're adding only integers from the data stream into our class, the median, again, could be evaluated from an even length list, which in that case would be the mean of two integers. So we want to use a double to return that. So as I approach this problem, the first perhaps naive method that you guys may think of is a more straightforward, relatively straightforward solution, which is that for add num, the data structure that we're going to use in our median finder object will be a list. The add num will just append the num to the list. And this find median method will sort this list and then return the element that occupies the middle element, or the median in that case, which we can find in O one time. So of course, that is ignoring the slightly added complexity of this list being even length, in which case we want to access the two middle values and return the mean of those two. But in general, for a brief sketch of this naive algorithm, it would just be maintaining a list, appending values to the list, and then every time we call find median, we would sort this list and then return the median elements. So in that case, add num would be an O1 constant time operation. However, find median would have this bottleneck of sorting the list each time, right? We would sort the list, access an O of 1, but sorting is that bottleneck, which leads to an O of n log n time complexity for find median each time we call find median. So how can we improve upon this? How can we make this more efficient? We already noted that the bottleneck was in this find median method, right? We saw that each time we wanted to call find median, we would have to sort the list, which was causing this inefficiency. The sorting of the list each time we just wanted to find the median element, we would essentially find the sorted order for every single element in this list, not just the median. We'd find the max, the min, third quartile, first quartile, median, we would sort this entire list, right? In this question, we're not concerned about sorting the entire list. We just want to keep track of this median element, right? So what data structure can we use to accomplish this? There isn't an immediate data structure that we know of, but there is a data structure that does accomplish something that's adjacent to our goal, right? A heap, a max heap, min heap takes in a list of values, but it will always maintain, or it has this property that the first element in this max heap will always be the maximum element or minimum element if it's a max or min heap. So we can always access this element in O of one time, the maximum or minimum. But there is no data structure that tells us the median element in O of one time. So how can we mold this max heap, min heap in order to accomplish our goal of keeping track of the median elements? In order to do that, right, the max heap or min heap only keeps track of the maximum or minimum elements. The median is at the exact middle of our list. In other words, the median is the minimum of the upper half of the list and the maximum of the lower half of this list, right? So what we can do instead is maintain two heaps. We're going to maintain a heap for the upper half of the list and maintain a heap for the lower half of the list. And each time we add an element to the list, we're going to absorb that inefficiency from find median. We're going to take care of sorting this list or keeping track of the median and add num. So that find median will just be an O1 operation, but add num will hopefully be log n if we implement this efficiently. So what we want to do is each time we call add num on an integer, a num, we want to add it to one of these lists, but we don't know which one yet, right? We don't know if it will belong to the upper half or lower half. And the invariant we want to maintain in add num is that the upper half and lower half both either have the same number of elements or one of them has one more. That way we can call find median and just take the maximum of the upper or maximum of the lower half or minimum of the upper half, or sum the two together and divide by 2 to find the median. So this algorithm that we are going to come up with, the efficient algorithm that we've come up with, is we're going to have a max heap and a min heap. So we're going to have two heaps. Each time we call add num, we're going to add a num. We're going to add this num to one of the heaps. We're going to do some load balancing and return nothing, right? Add num is a void method. Then with find median, what we're going to do is return the top of the lower half or the bottom of the upper half. We haven't decided yet which one is which, but that's an implementation detail, something we can take care of later. So we're going to return either the top half of the lower half or maximum element of the lower half of the list or minimum element of the upper half of the list. And if both lists have equal values, what does that tell us? That tells us that our underlying integer list is of even length, in which case we want to return the mean of the two. So we can just heap in our heaps, take the max of the upper half or max of the lower half, min of the upper half, and just find the mean of the two. So let's jump right into the code. So in our init method, as we talked about, we want to use a heap, right? So the first thing I'm going to do actually before I even dive into the init method, I want to import this heap queue class, which is what Python uses to implement a heap. So in our init method, we're going to have a self.lower half, and this will be a heap, and self.upper half, and this is also a heap. Then in our add num method, we want to add this integer to either of these lists. It doesn't matter which one yet, because right after we add it, we'll do our load balancing and take care of this property that the upper half or lower half. Upper half does contain the upper half of the list and lower half contains the lower half. So let's push this element num into the upper half of the list. And now that we've pushed num into the upper half, we want to take care of this load balancing. Now that we added something to the upper half, we should remove something from the upper half and move it into the lower half. So we can do this by taking the minimum of the upper half and just pushing this into the lower half. Not minus min upper. And now that we've done this, we should handle some load balancing and make sure both lists are even length. And in this case, as of right now, if one of the halves were to have more elements, it would be the lower half, right? So we're going to say while length of lower half so while this is the case, move elements from the lower half into the upper half. Let's not forget upper half and lower half are attributes of this class. So we want to make sure we're calling self dot for all of these. The reason I'm calling -1 times heap q dot heap pop as max lower is because Python, this heap q class, is a min heap by default. So in order to make this a max heap, I am pushing in the negation of the value. So when I push into the lower half, I want lower half to be a max heap, right? So I'm going to push in the negated value so that the negated value will be the minimum, because by default, the heap q class is a min heap. Okay, now that I've implemented add num, all that remains is to find the median. So based off this conditional statement, I can tell that if one of these halves were to be the larger half, it would have to be the upper half, right? Because if there is an odd length list, then right before there's equality, or right before we exit out of this if condition, this lower half will have one more element. And I move that into the upper half, and then this property is this conditional statement is no longer satisfied. So I exit the while loop. And because of that, the self dot upper half will have more elements, or one more element than the lower half. So if len of self dot upper half so if this is the case, I have an odd length list, so there is one middle value, and I can return this an O of 1 time. If this isn't the case, then I want to return the mean of the two. And I can do this by taking self dot upper half of 0. And again, because my lower half is a max heap, I want to first multiply by -1. Okay, this is our code. Let's run it and see if it works. Incredible. So here, let's go over the time complexity, find median. This is an O of 1 operation, constant time operation, and add num. Even though there is a while loop, because we only add one integer to either max heap or min heap, but because we're only processing one integer at a time, we're only adding one integer to our class at a time, this while loop will only run once. If we were to replace this with an if case or an if keyword, it would run the exact same. It would still work. So this add num method has 5 heap operations, and these 5 heap operations are all of log n operations. So add num runs an of log n time, logarithmic time. And this is a much more efficient algorithm than our naive implementation, which had add num or find median as O of n log n, whichever was absorbing that cost of sorting the list. So I hope that helps. I'll see you guys in the next video.